So first is the charger. Okay, this IC can achieve the charging of the battery pack. Okay, and in terms of charging, we can think of the buck converter here. Okay, this is a buck converter. Okay, this is buck converter. There is an inductor. There are two switches and the capacitor. Okay, so this is a buck converter. The buck converter input is from the adapter. Okay, from the adapter here. So this is an outside adapter, and the adapter will provide a DC voltage here. And this IC can control the adapter input. Okay, it can also regulate the adapter current. Okay, by this IC. Okay. There is a register. Okay, this is a current sense register, and this current sense register is fed back to the IC, so the IC can achieve the constant current charge for the battery pack. And there is a voltage feedback terminal here. This is a voltage divider. The voltage divider can feedback the battery pack voltage. Okay, so it can achieve the constant voltage charging. Okay, so the CCCV charging can be achieved. And there is a thermistor input here. Okay, this is a thermistor input here, and the thermistor can sense the temperature of your battery pack or other spot, other situation. Okay, and we read the description here. The voltage range can be from 5 to 28 volts, so it can support 1 to 6 battery cells, and it can provide the safety protection. If there is any safety hazard, then it can turn off the adapter input, or it can turn off the charging of the batteries. Okay, it can easily turn off the operation of the charging or the adapter input. And the battery thermistor sense can sense the temperature, so the too hot or too cold charge can be suspended, and the overcurrent can be protected because we sense the current, so the overcurrent is readily protected, and the battery short protection is also provided. Okay, data, we want to monitor the battery voltages, and then we maybe have to calculate to understand the SOC of the batteries and how to estimate SOC. Okay, here listed 4 methods. Okay, there are 4 methods here. The first one is open circuit voltage measuring. Okay, for a battery cell, maybe it can be modeled like this. There is a voltage source, and there is a series resistor, and there is a RC circuit here. This is a very simple battery model. Okay, this is a battery terminal. Okay, we can only sense the battery voltage here. This is an internal voltage source, and however, we cannot directly measure the voltage here because there are R and RC circuit here. Okay. If we model this circuit, we have a time constant because of the RC circuit here, and the terminal voltage will be the voltage plus or minus the voltage of this part. That means even though there is no current, the IE current is 0. there is no current. It will take some time for the discharging of the RC circuit. This is a time constant. Okay. This means for this battery circuit model, even though we stop the charging or discharging current of the battery, it will take some time to reach the internal voltage. This internal voltage is stabilized open circuit we just mentioned. It takes some time. And how long it will take? How long will it take? At least more than 30 minutes. Okay, at least more than 30 minutes. And more exactly, it takes several hours. In our experiment, we have done the experiment. Even though we wait for 2 hours, the voltage is still varying, but the varying level is very small, and the rapid varying will happen in the first 30 minutes. Okay. Anyway, it takes a long time. So, if anyone tell you you have to wait for 30 minutes to get the open circuit voltage and then you know the SOC, that is unacceptable. Okay. So, if we want to use this method, we have to find some method to do the estimation of the open circuit voltage first, and then we get the SOC readily. Okay. The second one is rough. I think this is a rough method. First, we try to get the internal resistance. Okay, we try to get the internal resistance. How to get the internal resistance? We just provide the current pulse into the battery. Okay, it provides a current pulse, and when the current pulse into the battery, there will be a voltage variation. And the voltage variation, we can, by the voltage variation and the current variation, we can get the internal resistance. And if we have the internal resistance, okay, if we have the internal resistance, then we can say, we can just measure the terminal voltage. Okay, we just measure the terminal voltage, and when there is a current flowing through your battery, and we can get the VT here, and we can estimate the voltage drop in the internal resistance. Because we know the current, we know the internal resistance, then we can estimate the voltage drop on this circuit. So by the terminal voltage, we can estimate the internal voltage. And the internal voltage is the open circuit voltage. Then we can have the SOC. Okay, so this is the second one. And yeah, maybe we don't have to get the precise open circuit voltage, because yes, now we just measure the so-called loaded voltage. Loaded voltage means there is current flowing through the battery, either charging or discharging. There is current, and the voltage measured on the battery terminal is called loaded voltage. And because the open circuit voltage is closely related to the SOC, if the loaded voltage is measured by the same current, okay, if the voltage is measured by the same current, then we can say the loaded voltage can also reflect the SOC. Of course, not so precise, but it can reflect. It is, to some extent, it just reflects the SOC situation. Okay, so this is the loaded voltage measuring. The final one is called current ampere hour counting, current counting or ampere hour counting. Okay, usually I will call it current counting method. The current counting method is integration of the current over time. Okay, so if we take the integration of the current, then this represents the charge deviation. And if we know the initial SOC, minus the voltage, the charge deviation, then we know the current SOC. Okay, so if the battery is charged, then the charge deviation will be negative. Okay, because usually the charged current is negative in convention, and when we discharge the battery, then the charge deviation will be positive. Okay, so we discharge, the SOC will be lower. When we charge, the SOC will be higher. And this is so-called current counting method. Current counting method usually is an effective one. Okay, this is an effective one because we don't measure the voltage. Even though the voltage has a flat voltage region, that is fine. However, I also have to say there are still some difficulties for the current counting method. The difficulty comes from, first, you can say, can you precisely measure the battery current? This is first. And the second is there any error of the time? Because we just integrate the current over time. You know, for the BMS IC, it can measure, it can sense the battery current cyclically. That means it can sample the battery current at a certain sampling rate. Okay. Usually, we assume that the sampling rate is constant. Okay, the sampling rate is constant. However, we can imagine that there will be some tolerance of the sampling rate. Sometimes in this cycle, the sampling rate is a little faster than the other one. That is very possible. So there is time error here. There is current error. There is also time error. So the integration maybe will be some error there. Okay. And there is also difficulty on the initial SOC. Maybe you do not know the initial SOC. Maybe you do not know, and you have to find a way to estimate the initial SOC. Okay. And there is a final difficulty there. That is, do you always expect that all the the current to charge the battery and all the electric charge will be stored in your battery? Usually we call it charge efficiency. Yes, for the lithium-ion batteries, the charge efficiency is very good. It's very good, nearly 100%. That means if we charge one current electric charge into the battery, then we can discharge one current charge out of the battery. It is very good, but still, it is not 100%. It's fine, but not 100%. And for other battery species, it is even worse. For lead acid battery, the charge efficiency is just about 90%. So every time you use a current counting, you have the charge loss during the charge or discharge. and that will make your SOC estimation deviated from the real SOC. Okay. But anyway, the current counting is a reliable one, unless you just notice there are some error sources, and you have to make the compensation for the errors. Then that's fine. Okay, so for this fuel gauge, it just applies the current counting to estimate the SOC. Okay, so it has to measure the current. Okay, the current will here. This is a current sense register, and the register will transform the current signal to voltage signal, and then feed back to the fuel gauge IC. Okay, so this just use the current counting method to estimate the SOC to fulfill the fuel gauge. And this supports lithium ion and lithium iron phosphate chemistries. As I said, this LFP is very difficult to know its SOC only by voltage. So by current counting method is fine. And the capacity estimation of this IC will from 3 to 65 volt. That means it can afford several series connected battery cells. And it can compensate the agent, so the self-discharge compensation and the support the battery capacities above for higher for a large battery cell, just like 65 per hour. This is a large battery. Okay. And then this is a cell battery monitor BMS IC. It can support the AFE monitoring feature. AFE means active front end. Active front end means it directly contact with the cells, so it can measure the cell voltages and other required features. And there are internal ADC to measure the cell voltages. Okay, the ADC, you know, the ADC is an analog to digital conversion. Okay, it has an internal ADC to transfer the measured analog cell voltage into the digital numbers, and the die temperature and the external thermistor. So it can measure the voltage, the temperature, and the external temperature of the IC. And there is a separate internal ADC to measure the pack current. So voltage and the current, they are separated, and the pack current can be used for the current counting. And the hardware can protect from overcurrent, short circuit, or over voltage or under voltage. And it has internal integrated cell balancing FET. FET means the switches. The switches, they can be used for the cell balancing. And there is a charge discharge low side N-channel FET drivers. For the FET switches, we need the drivers, and this IC provides the driver itself, and it can supply a high voltage. Okay, this is IC. For this IC, there are several pins, and these pins can be connected to the cells. Okay, they connected to the cells, and there are RC circuit here. The RC circuit here, actually, they are low pass filter. They just used to filter out the high frequency noise. Okay, and you can see here for the VC0 actually should be the lowest terminal voltage. Should be the voltage here, but there also is a RC low pass filter here. to filter the VC0 voltage. Okay, and there is a current sense register for sense pack current, and these two switches are the so-called charge with the discharge low side N channel FET. They are these two switches, these two FET switches, and they can be driven directly by the IC itself. Okay. When we want to charge or discharge the battery pack, of course we have to turn on these two switches. Okay, that means if we want to terminate the operation of the battery pack, we can just turn off these two switches. Okay. So it can cut off the current. So as I said, there are no the actions the BMS IC can take actually is limited. These two switches is action it can take to protect the battery pack. This BMS IC, there is TS. TS usually means thermistor sense. So this terminal is used to sense the temperature. Okay, and there are SCL and the SDA. These two pins are used for the I2C or SPI communication. So this is a communication to the other companion controllers. Okay, so this is a control IC. For the layout of the BMS IC, there is some suggestion here. Here we can see this is the ground. Okay, so this is the battery, the lowest voltage of the battery pack, and it is connected to the ground. The ground is different from the pack. Okay, this node and this node are different because there is a voltage variation of the current sense voltage and the voltage drop of the FET. So these two nodes are different, and we say this is the ground. Okay, and this is ground, and for the VSS, this is also ground, and there is a regulator. Regulator is connected to ground. Okay, there are two regulators. They are also connected to ground. So we have several pins. They will connect it to ground. And yes, this is battery minus, and this is current sense. Okay, this is battery ground. This is battery minus. This is current sense register. This is the same node, you know. This is the same node. However, if our layout just connect these pins to the trace here, okay, if they directly connect to the trace, you know, this is a pack current. The pack current will flow through this trace, and the pack current usually is very high. If the high current flows through the trace, you know, there is resistance on the trace. Even though the resistance is not so high, however, the current is high. So the voltage drop here is apparent. You cannot just ignore the voltage drop. And the voltage drop will make you just expect that all these terminals will be connected to the same voltage node, but they are not. Okay, so the good layout convention will be like this. All the terminals are connected to a separate trace. This is a separate trace. that is not the PCB trace of the battery minus to the current sense. So in this trace, there is no high current. Okay, there is no high current. So the voltage drop here can be ignored. We can just think that all these pins are connected to the same voltage node. Okay, so this is a reminder of the layout. And there is also another reminder from the data sheet. That is, if your battery module contains many cells, and because of the assembling requirement, maybe some cells are closely assembled, while the other cells are remotely assembled, like this. These cells are closely arranged, and these are separated. So there is a long connection here. Okay, and again, we have to notice that there is high current flow through these connections. So the connection here might be a lot of voltage drop. And how to deal with the voltage drop here? The suggestion is you just think that the voltage drop is another voltage cell. Okay, you just take this as a voltage cell. So it is connected to the pins here. So the BMS IC will get the cell voltage, and this one. And of course, the BMS IC can understand this is not a real battery, and it can discard the voltage drop here. Okay, and I want to talk about the balancing feature of this BMS IC. You can see here inside the BMS IC there are some internal FET here, and this FET can short circuit the pins, the neighboring pins. Okay. And if we just connect external registers to these pins, when we turn on this switch, we can just discharge the battery cells to achieve the energy dissipation equalization method. Okay, we can use these FETs to achieve the function. However, you also have to know that because these are intrinsic FET, the current flow through this FET is limited. That means if you want to dissipate your cell to achieve balanced state, it takes a very long time, and maybe that is not practical. So the more practical method will be an external balancing. The external balancing means we use an external FET switches. Okay, we can choose an N-channel external switches or P-channel external switches. If we use the N-channel, okay, here, you know this is RC low pass filter. Okay, this is a low pass RC filter. This is another low pass RC filter. If we want to discharge this battery cell, okay, if we want to discharge this one, we just short circuit the internal FET. Okay, we turn on the internal FET and short circuit these two pins. and the short circuit will result in a current flowing through this loop. And the current flowing through this loop will result in a voltage drop here. There will be a voltage drop here, and the voltage drop here can provide the VGS of the N-channel MOSFET. Then it can turn on this external MOSFET. Then it will provide a dissipation loop, a dissipation path here. So the battery energy will be dissipated on this resistor. Okay, and because this is an external MOSFET, it can flow through a higher current. So the energy can dissipate on this resistor is higher than the internal balancing method. Okay, so this is more practical. And also you can use a p-channel MOSFET here. If this is p-channel MOSFET, then you have to provide the VSG. You have to provide VSG to turn on this p-channel MOSFET. In this way, if we short circuit these two pins, then the current flow again within this loop, and the voltage drop here will provide the positive VSG for this p-channel MOSFET. And this turn on the MOSFET and it provides the discharging path. Okay. So this is external balancing provided by the BMS IC. And this one actually is a gate driver. Okay, this is a gate driver. I just mentioned that actually to drive the switches is a difficult issue, because the VGS of the MOSFET, actually there are different voltage levels. They are not commonly ground, so we have to equip many voltage source for the voltage driver, and that is not very easy. And so this IC just provide the gate driver for the switch matrix. So maybe it is easier. We can just check this. This is a gate driver IC. Okay, this is a gate driver IC, and it can drive the switch matrix here. Okay, it can drive the switch matrix here. That means it can provide different voltage levels, voltage sources for the MOSFET here. Okay, and this topology actually is this one. Okay, this is a method presented earlier, and this IC is used to implement that kind of charge balancing method. Okay, just now they are the TI solution, and there are also other manufacturers like this one. This is a linear technology. Okay, and this LTC6804, this is also a active front end. Okay, so it can measure the battery cell voltages and the current and temperatures. Okay, the features are listed here. There are 12 battery cells, and it can be stackable to support more battery cells. And the measurement error is very limited. And there is 16-bit ADC, so the resolution of the ADC is very high. It can provide a passive cell balancing. This is a block diagram of the IC. You can see the terminal, the pins here. the pins here provide the active front end to monitor the cell voltages. And here there are internal balancing FETs. Okay, so it can provide the similar functions we just introduced, like from the TI's BMS IC. It says that it can achieve the stackable topology to achieve more series connected cells. The stackable is achieved by this way. You can see here. This is address. Okay, this is address. That means this BMS IC can use the address to locate a specific BMS IC. And you know, the BMS IC here, actually their voltage level are different because they connected to the battery cells, and the battery cells are serially connected. So the voltage level into the BMS IC, actually they are different. So they require the isolation here. If you know, we want to communicate between these BMS IC. We want to send the signal from the master MCU to a specific BMS IC. Yes, we can use the address to locate the BMS IC. We can send the signal to a specific BMS IC, but their voltage level are different, and the voltage isolation function should be provided. Otherwise, there will be a short circuit between them. Okay. And this IC is also provided by the linear technology, and this is actually is a so-called monolithic flyback DC to DC converter. Okay, let's check. Let's check here. This IC has a internal switch. There is an internal switch, and this IC can operate its own switch to provide the flyback conversion function here. So for each cell is connected to one flyback converter, and the output of the flyback converter is connected to the Hall module. Okay, it is connected to the Hall module, so it can achieve the cell to module energy transfer. And the flyback converter is directly controlled by this IC. Okay, so this is an easy way to fulfill the flyback operation here. And actually, this is an implementation of this method we just introduced. And this should be the final one. Okay. For this IC, we just check the topology. For this IC, it can connect it to 6 cells. Okay, this IC can connect it to 6 cells, and for each cell, it is connected to a bidirectional flyback converter here. For each cell is connected to an flyback converter, bidirectional flyback converter, and the flyback converter can be operated directly by this IC. Okay, so it can control the turn on, turn off of the switches here. The connection, let's check the connection. For this cell, it connected to this flyback converter, and the output of the flyback converter is connected to the whole pack. Not the module, but the whole pack. Okay, so it can achieve the pack to cell or cell to pack energy transfer, and it is this method. Okay, so you can see uh, some fabricated method actually can be supported by some specific BMS IC. Okay. Okay. That's the end of this session. I think it is a little lengthy. Okay. I can see it is not very easy for you to focus on the introduction, but anyway, as I said, charge equalization is a very important issue for the battery management, and it is not unified. It cannot readily provided by the BMS IC. Although here some BMS IC do support, they can support some specific topology, but not all. And of course, this topology cannot fit for all the applications. So always you have to propose a suitable topology for your battery pack, especially for the higher voltage battery pack. The 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 charge equalization issue is more important. It's more important because the high voltage will require a higher capacity, longer service life, and we hope uh, the energy dissipated between the charge equalization operation is reduced. So we have to pay more attention to how to achieve the charge equalization. And this is what we can do the research. This is the issues that we can do the research on. And for the BMS, for the other tasks of the BMS, actually we cannot. There is no space for us to do the research because for us means power electronics guys. There is no much room for us. There is more room for the IC design guys. They can do more on this topic. And for us, the power electronics guys, we can focus on the charge equalization issue. Okay. Okay, this is the end of today's lecture.